Great, I'm glad you can hear me. All right, so let me get our slideshow started. All right, so there's our slideshow. Actually, before I get started myself, does anybody have any quick questions about anything? Okay, I'm not seeing any questions. Go ahead and ask while I move on, and then I'll answer them if I can. A couple of announcements to start with. One is that the Science and Math Peer Tutoring Program begins today. I don't know if you guys are aware of this, but this is a program that offers free tutoring. Currently, it's operating online in actually in Canvas and BB Collaborate. There's if you want to sign up for it. So this is undergraduates who have recently taken first year physics or math or biology in the last year or two and now volunteer their time. These are volunteers, remember, they volunteer their time 4 hours a week providing tutoring, drop-in tutoring. And so if you go to the website listed there, you'll see the hours, and there are tutors there who tutor physics 120, 121, and various biology courses and chemistry, and even some math tutoring there. So that's a place where you can go for help if you have a question and you weren't able to make it to my office hours, or you weren't able to make it to the TA's office hours. Just to point out, my office hours are now back to the regular time. So I will have an office hour today at 1 to 2 p.m. And I also wanted to mention that if you can't make my regularly scheduled office hours, you're always welcome to email me, and we can set up a different time. We can make an appointment to have a chat in BB Collaborate if you have questions. And then yet another reminder to please purchase your Achieve Access soon, because if you've got the free access, it's likely it's going to expire soon. Get the 2-term access if you're planning on taking Physics 121. And also a reminder that we're going to start using iClicker next Monday. So you should try to get that set up. Okay, so there was a question about so 1/2 AT squared, and when does it become negative or positive? So so that basically in one dimension, right, then A, right, can either be positive or negative, right? It's the A in that part of the term, okay, depending on whether the acceleration, right, points in the positive direction or the negative direction. And then when you get to 2 dimensions, right, then it becomes AX or AY. And so then it depends on whether the component, the X or the Y component of the acceleration, is positive or negative. So the sign is contained inside that component. That's how I would explain it. So basically, yeah, it's telling you the direction of the acceleration. Okay, so what are we going to do today? So today is, you might have noticed, so today is one of our problems and demos days. So we did not have a pre-lecture for today. So we're going to do some more problems and one demo on some of the topics we've already covered. So we're going to have some poll questions and some example problems on circular motion, on 2-dimensional motion, and if we have time, on motion graphs. I've got a bunch of stuff in here. We'll see how much, if we have time to do all of it. If we don't have time to do all of it, I'll post the rest of it so that you can at least see it and see the answers. So we are going to start with a poll question on the topic we did last time, which was uniform circular motion. So I'm going to start our poll here. We got 5 choices. You can have a look at this while I start it. Okay, so there's our poll. So what have we got? So you can see we have a little red ball. It's moving counterclockwise and it's undergoing uniform circular motion. And the question is, as the ball passes the point shown, okay, so where it is at that angle theta, what's happening to the y component of its acceleration? So is the y component of its acceleration negative and becoming more negative? Is it negative and becoming less negative? Is it positive and becoming more positive? Or is it positive and becoming less positive? Okay, or is it constant? And you should look at the upper right. I've defined the y direction to be upwards to be positive, and the positive x direction to point to the right, which is what we typically do, right, for x and y. So think about what the acceleration of an object in uniform circular motion, what the acceleration looks like, what kind of acceleration we're talking about here. Okay, remember uniform circular motion means you are moving at a constant speed along a circular path. And we're trying to figure out what's going on with the y component of the acceleration here. All right, I think we're going to do 10 more seconds on this one. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. Okay, so at this one, it looks like this one is a little confusing. Okay, we've got not a completely flat distribution, but lots of different possibilities here, lots of different choices. All right, I'm going to leave the poll up for a second, and I'm going to start going through the slides and through the slide and the explanation. And if you feel like changing your mind, okay, as we go, I'm going to let you try and do that. I think you should be able to change your mind. I'm not positive. So first of all, what does the acceleration look like for an object in uniform circular motion? It looks like that, right? This is centripetal acceleration, right? It points towards the center of the circle. Okay, so that vector, does that vector have a positive y component or a negative y component? Anybody want to guess? Yes, that has a negative y component, right? Okay, so that means, right, that the answer has to be either A or B. Okay, so actually, I think we'll just go through the explanation. I'm not sure if you're allowed to change your answer here, so I think we'll just go through the explanation. Okay, it looks like, so we know the answer has to be A or B because that's negative, and then as the object moves, as that little red ball moves, right, a little time later, for example, it would be there. Okay, it would be at the top of the circle, and that acceleration vector has an even larger, in the negative direction, y component. Okay, right, the y component there has gotten bigger, and the x component, right, in the negative direction is getting smaller. So in fact, the answer is that the y component is negative and becoming more negative at that point. Okay, remember we're talking relative to the axes shown above, right, where I defined positive y to be upwards. So questions on that? Because it's going to be have a negative y component, become more negative, and then once it reaches the top, that'll be the max negative component, and then it'll start becoming less negative as it goes around the circle. All the slides today, yes, will get posted. All right, so what I thought we would do now is do an example problem for uniform circular motion, mostly so you can see how the math works for one of these problems. Okay, why is it more negative? Okay, because you can see that the y component there, right, for say the second vector is bigger than the y component in the negative direction than for that first vector. Okay, that y component has increased. It became more along the y-axis and less along the x-axis. All right, so we're going to try and do an example problem here. So say for your circle, the radius is 5 meters, the speed of the ball is 15 meters per second, and that angle theta is 70 degrees. What we're going to figure out, what are the magnitude and direction of the centripetal acceleration? What are the x and y components of the centripetal acceleration? And what is the angular velocity omega of the ball? Okay, that's what we're going to try and figure out here. And so what I'm going to do is switch to my document camera, and hopefully that will work here. All right, so first question that we're trying to figure out the answer to is what are the magnitude and direction of the centripetal acceleration? So we know that the definition, or one way to calculate, maybe not the definition, but one way to calculate centripetal acceleration is that it's equal to v squared over r. So that's pretty straightforward because we have v and we have r. So it's going to be 15 meters per second squared over our 5 meters. Okay, and we end up with a centripetal acceleration. The magnitude now is going to be 45 meters per second squared. So that's our magnitude. Pretty straightforward. Okay, and then as we saw before, if we draw it in, right, this was 70 degrees. Right, and we know it points this way. That's our centripetal acceleration. Okay, and we know that this is the y direction, this is the x direction, like that. So we know if that's 70 degrees, then this angle up here is also 70 degrees. That's one of our geometry rules, right? That if you have two parallel lines, those two angles would be equal. So the way I would write the direction here, just to be completely clear, is I would write it as 70 degrees below the minus x axis. Okay. This angle is 70 degrees. This is the minus x-axis, so it's 70 degrees below the minus x-axis. That would be the complete way to specify that angle. You could also, like I said, as long as you draw a picture that specifies where your angle is, you're also good for specifying your direction. Okay, so that's our magnitude and direction, and now we want to figure out our x and y components. So AX here, so you can kind of see it. I'm going to draw it a little bit bigger down here, just so we can see it. So this is our centripetal acceleration. So this would be AX, okay, technically in the I hat direction, right? And AY and the j hat, right? And where this ax and this ay now are going to be negative quantities, right? Since they point to the left and down. Okay, so that means that ax is going to be minus the magnitude, and since this is our angle theta, that's our 70 degrees. Okay, so it's going to be minus the magnitude times the cosine of theta. So that's going to be minus our 45 times the cosine of 70. Okay, which gives you minus 15.4 meters per second squared. Okay, for the x component. And then if we do the y component, now the y component we get is minus the magnitude times the sine of the angle. So minus 45 times the sine of 70, right? Which gives you minus 42.3 meters per second squared. So there are our two negative components there for ax and ay. Okay, so that means if you wanted to write this acceleration in unit vector notation, it would look something like this. It would be minus 15.4 I hat minus 42.3 j hat meters per second squared. You always want to include the units there when you're writing things, an actual physical quantity in unit vector notation like that. Okay, so that's our acceleration vector, our centripetal acceleration vector. And then the last part, we just want to figure out what's omega here. What's the angular velocity? Remember, omega is d theta dt, how fast the angle theta is changing with time. And you can calculate it by just taking the speed and dividing by the radius of the circle. So for us, this is 15 meters per second divided by the 5 meters. Okay, and so now the meters cancel out. 15 over 5 is 3. And all you get left from the units here is per seconds. And this is one of those cases where you have to stick the radians in. So we stick in the radians because we know if you're calculating omega from V over R, that you're going to get an answer in radians per second. So this is 3 radians per second. That's our angular velocity for this object. So any questions on how any of that worked? Okay, so now what I'm going to do is we're going to switch back to our slideshow now. So we're going to stop this. There we go. We'll stop that. And we will go back to our slideshow. Okay, so we answered all of those questions. We did our uniform circular motion example. So now we're going to do a two-dimensional motion example, another two-dimensional motion example. Okay, I'm going to switch here. Okay, so let's read about this example. This is one I put on a midterm recently. So give you an idea, the kind of thing that possibly could show up on a midterm exam. So we have a cat that runs across a field on which a set of coordinate axes has been drawn. How convenient. And the coordinates of the cat's position as a function of time are given by the two equations shown below. Okay, so we've got x is a function of time here and y is a function of time. Okay, and they tell us that time is in seconds and x and y are in meters. So there's 3 questions. The first one is, what are the x and y components of the cat's velocity as functions of time? The second part is to find the velocity of the cat at 2 different times, time equals 0 and time equals 8 seconds, and express your answers in unit vector notation. So more practice with our unit vector notation. And then the last part is to determine the average acceleration of the cat between time equals 0 and time equals 8 seconds. And again, express your answer in unit vector notation. Great, okay. So before we dive into this, in fact, what I'm going to do is have you see if you can figure out the first part. So we're going to have a poll for this. So why don't you go ahead and have a look at that question, and I will start the poll. Jasmine, you have a question? Do you want to ask it in the chat? All right, so what's our question here? So this is part A. The question is, what are the x and y components of the cat's velocity as functions of time in meters per second, which is our unit system here. So you can see for each of those choices, except for the last one where it says none of the above, there's a Vx and a Vy, so that we've got the x component and the y component of the velocity of the cat. So the main thing to think about here is how do you get from position as a function of time to velocity as a function of time? All right, let's do 10 more seconds on this one. So if you're not sure, go ahead and guess. All right, 5, 4, 3, 2, 1. All right, and what do we got? So a lot more agreement on this one than on the last poll. So the vast majority here are going for A. So let's see how you would figure this one out. All right, so the main thing to remember here is the way you get from position to velocity is that you have to take a derivative with respect to time. Okay, so for example, if you want to figure out the x component of the velocity, that's equal to dx dt. Okay, and so when we take a first derivative here of our polynomial, remember with the t squared, you bring the 2 down in front. Okay, so you get 2 times minus 2.5, and then for the second term, right, you get basically t to the 1, right? So you bring a 1 down and you get t to the 0. So basically the derivative of 6t is just 6. And then the derivative of a constant, minus 15, is 0. So we don't get that term at all. And so we end up with minus 0.5t plus 6 for the x component. And then if we do the similar thing for the y component, that the y component of the velocity is the first derivative of the y position with respect to time. So you do each one independently like this. Okay, and again, you bring the 2 down. It's 2 times the 0.5 times t to the 1 power, which is t, and then minus the 2.5 times t to the 0 power, which is 1. Sorry. And then the first derivative with time of the constant 24 is 0. And so you end up with 1t minus 2.5. So that's just doing our first derivatives. And so most of you did that quite well. And you got that the answer was A. For you, those of you who are new to calculus and are still learning derivatives, like I said, way back, I think on our second lecture, these are the hardest derivatives probably we'll do, at least up to this point. A little bit later on, we'll do some derivatives of sines and cosines, but we won't go beyond that pretty much for the most part. Okay, so any questions on that? So that's how you would figure out the first part of this question. So now what we're going to do, that was the first part, okay, is we're going to go back. I'm going to go back and do the rest of this problem. Okay, so we've done A. Okay, and so now we're going to do B. We're going to find the velocity of the cat at time equals 0 and time equals 8 and express our answers in unit vector notation. And then we're going to figure out the average acceleration of the cat. So I'm going to switch back to my document camera. Okay, so B says we're going to figure out what's the velocity at time equals 0 equal to. That's half of part B. We're going to find the velocity at 2 different times. Okay, so literally all you do is first you start with the 2 components and you plug in time equals 0 into the expressions we just saw. So that means that the x component is minus 0.5 times 0 plus 6, which will be 6 meters per second. Basically, you're just going to get that constant term. And similarly, the y component will be 1 times 0 minus 2.5. So that's going to be minus 2.5 meters per second. So that's the initial x and y component. Of our cat. Okay, so it's moving 6 meters per second in the x and minus 2.5 meters per second in the y. And so now in unit vector notation then, v at 0 would look like this. It would be 6 meters per second I hat minus 2.5 meters per second j hat. That's another way you could write unit vector notation. You can either stick the units on each term or stick them at the end. Either way is fine. Okay, now we're also going to figure out what is it at time equals 8 seconds. So again, you just plug in 8. So the x component at 8 seconds is minus 0.5 times 8 plus 6. And minus 0.5 times 8 is minus 4. So this gives you 2 meters per second for the x component. And then we can do the y component. Okay, and the y component then will be same formula as above, 1 times 8 minus 2.5. 1 times 8 is 8 minus 2.5, you get 5.5 meters per second. Okay, so the cat has lost speed in the x direction, right? Went from 6 meters per second to 2, but turned around in the y direction, went from minus 2.5 to plus 5.5. So I hat and j hat are unit vectors that point along the x and y axes, okay, and we use them to designate directions here. Okay, so here, if you wanted to represent the velocity at 8 seconds, you would write it as 2 meters per second I hat. So that's a vector that's 2 meters per second long that points in the positive x direction. And then it would be plus 5.5 meters per second j hat. So that's a vector. This term is a vector 5.5 meters per second long that points in the positive y direction. That's what that tells you. Okay, and that's what your unit vector notation is going to look like here. So that's part B. Now for part C, we want to figure out our average acceleration between these two times. Okay, so our average acceleration for time equals 0 to time equals 8 seconds. All right, and so we just go back and we say, okay, what's our definition, okay, of average acceleration? It's delta v over delta t, where delta v is the change in velocity. And remember, change in velocity means doing a vector subtraction. You take the final velocity, which in this case for us would be the velocity at 8 seconds, minus the initial velocity, which is the velocity at 0 seconds. So we're going to do that vector subtraction, and then we're going to divide that vector subtraction by the time elapsed, our delta t, which for us would be 8 seconds. Okay, so let's start with the top part. So we've got the velocity at 8 seconds minus the velocity at 0 seconds here. So I'm going to write down my two vectors here as in their unit vector form, so you can see how you might do it with unit vectors. I'm going to leave off the units for now. So the final velocity is 2 I hat, okay, plus 5.5 j hat, right? That's my final. And then I'm going to subtract 6 I hat minus 2.5 j hat. Okay, so that's how you might write vector subtraction using unit vectors. Okay, and then what you want to do is combine terms. Okay, so I'm going to basically say I've got a 2 I hat and a minus 6 I hat. So that means I have a 2 minus 6 times I hat. That's going to be my x component. Okay, and then I've got a 5.5, so plus a 5.5 minus a minus 2.5, minus a minus 2.5 in the j hat direction. Okay, so this is one of the reasons unit vectors are useful, because now you can do this kind of calculation like this. Okay, and it makes it pretty straightforward. So what does this become? 2 minus 6 is minus 4. So I'm going to have minus 4 meters per second in the I hat direction. This is, remember, this is our change in velocity now. This is how much the velocity is changing in 8 seconds. Okay, and then this is going to be positive 8. So plus 8 meters per second j hat direction. So that's our change in velocity for the cat for that 8 seconds. And then to get the average acceleration vector, I'm just going to divide both terms by our time elapsed by our 8 seconds. Okay, and so I divide both of these by 8 seconds. Okay, so I'm going to have minus 4 over 8 I hat, right, plus 8 over 8 j hat. And so that's going to give me minus 0.5 meters per second squared now, right? Because we divided by a second. I'm running out of space here. I hat, right? And then plus 1 meters per second squared j hat. So that is my average acceleration. I'll put a box around that one, see if I can make it so you can see that a little bit better now. That's my average acceleration. Okay, so that's how you might figure that one out. Now, some of you might have noticed, looking at those original two equations for x and y, that they were both parabolas. And if you have parabolas for position versus time, then that tells you that the acceleration is constant. Okay, so just to flip to a new page here, that this is actually, so if x and y are parabolas, right, as functions of time, then that means that ax and ay are constant. Okay, and you can see that pretty easily by basically calculating our ax and our ay. Okay, so ax would be dvx dt, the first derivative with respect to time of the velocity with the function of time. Okay, and remember that was minus 0.5 t plus 6. And so that just gives you minus 0.5 meters per second squared. So there's a constant x component, okay? And if you do the same thing in the y direction, dvy dt, you take the first derivative with respect to time of the y component, which is 1 times t minus 2.5, and you get 1 meter per second squared for your constant y component. Okay, and if we go back and look, okay, at what we got for our average acceleration from before, we got exactly those two numbers. Okay, because if the acceleration is constant, then the constant value should be equal to the average, right? The average is always equal to that constant value. Okay, so let's see, there were a couple of questions here. No, you need to use I hat and J hat, okay? Because we're learning how to use the I hat and J hat representation. Okay, so no, you can't use brackets. I want you to use I hat and J hat, okay? Well, you divide by the time frame given. So you were asked to find the average acceleration between time equals 0 and time equals 8. So we looked at the final velocity after 8 seconds. We subtracted the initial velocity at time equals 0. And so then you have to divide by the time elapsed for that time frame. Okay? But yes, I do want you to use, the only other exception is sometimes people write this. Instead of I hat, they write X hat, or instead of J hat, they write Y hat. I would be okay with X hat and Y hat instead of I and J, but there are going to be problems that use I and J. Okay, so you have to get used to it. How do we know it's a parabola? So if we go back now and share our slideshow, I'll stop sharing this. Okay, and we'll go back and share our slideshow. We can see it's a parabola, okay, because it goes as time squared, okay? All right, x, the highest power for the x is time squared, and the highest power for the y is time squared. Okay? So, no, I'm not going to go over 12 from the homework. Once the homework has been submitted and achieved, you will be able to see an explanation of it because there'll be an answer, a completely solved solution in Achieve. And if you would like me to go over it, I'm happy to do that during office hours. But I would like to do different problems now rather than go over one you've already had and we'll get a solution for. All right, so now we're going to skip forward and do another one. This is our probably be our last one for today. This is one you may have seen before, but just in case you haven't, I thought it would be fun to look at this problem. This is a classic physics problem. Okay, it's called the monkey drop problem or the monkey shoot problem. Okay. And the question is, so you are a vet and you're trying to shoot a tranquilizer dart into a monkey who's hanging from a branch in a distant tree. You know that the monkey is very nervous and will let go of the branch and start to fall as soon as the gun goes off. So here's the gun, gonna let go. Okay, as soon as the bullets, the dart, sorry, the tranquilizer dart starts heading for the monkey, he's gonna let go, or she's gonna let go. And the question is, where should you point the gun before shooting if you want the dart to hit the monkey? Should you fire right at the monkey? Should you fire below the monkey? Or should you fire above the monkey? Yes, my office hours are 1 to 2 p.m. and BB Collaborate. They are listed in Canvas. When I say point at, what I mean is if you're standing there and you see the monkey up in the tree, okay, you're going to point right at where the monkey is up in the tree. And then fire. And right as you fire, the monkey lets go. So I mean, so you basically eyeball where the monkey is. And aim right at it. All right, let's do 10 more seconds on this one. So if you're not sure, go ahead and guess. Hardika, did you have a question? I think you have your hand up. I'll answer your other questions at the end, you guys. I want to try and make sure I get through the rest of this first. All right, 5, 4, 3, 2, 1. So let's see what everybody thought. All right, so this one, again, was a little confusing. We do have a slight majority are going for B, that you should aim below the monkey. Okay, but then our next biggest group says that you should aim right at the monkey. All right, so let's see how you would figure this out. So the way we're going to figure this out is we're going to use our two-dimensional kinematics, okay, which we're getting lots of practice with here. Okay, so this is what it would look like. This is what I meant by point right at the monkey. Okay, so there's a monkey at height h. So the monkey's starting there at y equals h. Okay, and the dart, the little green thing, is starting at x equals 0, y equals 0. All right, so we're trying to figure out what is the right launch angle here, theta, such that the dart will hit the monkey. Okay, so this is what it would look like if you aimed right at the monkey. Okay, so what do we know? What we know is that as you fire the dart, it's going to travel to the right and it's going to go up and then come back down again. That's our projectile motion. And what we need is for the dart to be at the same vertical position as the monkey when the horizontal position of the dart is D, right? Which is the horizontal position of the monkey. The monkey's horizontal position isn't going to change because the monkey's just going to fall straight down. Okay, so we need that dart to be at the same Y as the monkey when it gets to D in the horizontal direction. So we're going to do our kinematics. So let's start with the dart. So this is our Y position kinematic equation, right? And what we're going to do is put in everything we know for the dart, which is that we know that the dart starts at Y equals 0. Okay, so we get Y dart is equal to V0YT. Okay, the Y component times time minus 1/2 GT squared, right? And it's minus 1/2 GT squared because the Y component of the acceleration is minus G. All right, and we know the X equation, the X position equation for our dart, okay, would be x0 plus v0 xt. There's no acceleration in the x direction. And again, the starting position, x0 is 0. And the final position we're looking at here is d. And so we get that d is equal to v0x times time. So that means we know one thing already, that the time it's going to take to get to x equals d is just d divided by the x component of the velocity. Okay, so that's one thing we know, is how long it takes the dart to get to x equals d. All right, now, okay, let's do the monkey. All right, so the monkey, this is the monkey's y position equation. Okay, the y of the monkey is equal to its initial y, which is h. Okay, the monkey has no initial y velocity, so you lose the second term, and then we get a minus 1/2 gt squared because the monkey also is going to undergo acceleration due to gravity. All right, and so what we're going to do now to figure this out is we're going to set the two y's equal. Remember, the two things have to have the same y at the time when the dart gets to x equals d. So we're going to set the two y's equal, y monkey equals y dart. And what happens when you do that? So we set our two y expressions equal to each other. And one thing to notice right away is you get minus 1/2 gt squared on both sides. And since you get minus 1/2 gt squared on both sides, they cancel out. And so we end up with a really simple expression here that the height, okay, of the monkey has to be equal to v0y times time. And then we plug in the time when the dart gets to D, because that's when we want the two y's to be equal, and we discover that the two objects will be at the same y at this time if h over d is equal to v0y over v0x. Okay, and what that means is that the ratio of h to d has to be the same as the ratio of the y component to the x component of the velocity, which means that the angle theta has to be the same for both. That means that you have to aim directly at the monkey, right? So in other words, that v0y has to point along the line that goes from the origin to the point DH, right, where the monkey is located. It has to point along that line in order. So basically what's happening, you can kind of watch what happens, is over time, okay, once the dart is fired, both the dart and the monkey fall. So the dart falls away from the line it would have followed if there were no y acceleration, and the monkey falls, and they both fall the same amount in each time interval, and so the dart hits the monkey. Okay, so basically, the answer is that you have to fire right at the monkey. Now, we've run out of time, unfortunately, and I wanted to show you a video of this. So I'm going to go ahead and play this. I realize some of you are going to have to go, but I will also post this in Canvas for you guys to see later. So this guy is going to actually shoot a monkey for us. Okay, we like to do this one live, unfortunately, since we're not in person. So there's our monkey. Okay, and the first thing he's going to do is use a laser. Well, he's going to raise the monkey. There he goes, going up. Here's the monkey cam. This is kind of cool because he has a camera on the monkey. Okay, and then he's going to use a laser to make sure he's aiming right at the monkey. So there's the laser point. So he knows he's aimed right at the monkey. And then he's going to fire his dart. So there's our monkey, and he fires. Okay, so now it's kind of hard to see there. All right, that he actually hit the monkey. So he's going to do it again in slow motion. So there you can see that the projectile there actually hit the monkey. And then they go through and show you a bunch of different views. You can see it there, that you hit the monkey if you aim right at it. Okay. And there's another view with a lower speed. So they go through and try a bunch of different speeds. So like I said, I'll post this. And here's the slower speed again. There is a minimum speed required. If your speed is too small, then you won't get to the monkey. So that can be a problem. All right, so like I said, I'll post a link to that so you can play around with it. I'm going to stop our recording now.